Okay, I want to start with an announcement that revised edition of mathematical puzzles is free online. Please write this URL down. There it is.
You can just Google Winkler puzzle book.
Yeah, you could do that. You could Google Winkler puzzle. There's the first edition is sort of a shocking pink. This one is blue. And yeah, and if this book is any good, it's due to people like Dr. Knuth and Richard Stanley, who sent in puzzles and later sent in better solutions to puzzles. And so this book is actually a joint work of all of us. Okay, and in this book you will not find the following puzzle. Let X and Y be random variables that are uniformly random on the unit interval. It's as simple as continuous random variables get. And I want to know what sets in the unit square can be in support of their joint distribution. So here's the square. Think of X as being distributed uniformly on the bottom and Y on the right side. And I give you a set here. Could this be exactly the set, or literally the closure of the set of all points X, Y that can occur when you actually words couple X and Y together in a particular. Okay. So let me restate that in even more general fashion. I think this is a fundamental problem in probability theory. We get into distribution mu and nu. That looks like a V, doesn't it? It's a nu in this type. Say on a real line. And when that's the support of a joint distribution is marginal to mu. And what does the discrete version of this look like? Well, the discrete version is going to look almost elementary familiar. You're given a set of row sums, right? Those are your one distribution, and a set of column sums, hopefully with the same sum. And you're given a template matrix, just a 0, 1 matrix. And what you want is to find a matrix which has those row and column sums and is non-zero exactly where your template matrix is non-zero. If you ask for exact, we just ask for it to be positive only where the template is positive, we have a very familiar, easy combinatorial problem which we can solve with Paul's marriage theorem or even less, or Maxwell and cuts. The continuous version can be translated to this, and I'll explain how in a minute. We're looking for a closed, we were given a closed subset of the unit square. A permuton is exactly a probability distribution on the unit square with uniform margins. So it's exactly the joint distribution of two uniform unit squares. And the question is there one who supports exactly this? So maybe I actually hope you're thinking what I was thinking, which was that this has got to be known. It's got to be easy too. As far as I know, I was 0 for 2 on these lists. Right, let's take a look at a little bit more. Okay, so first of all, what is permuton again? It's a say probability distribution on units, a real distribution, uniform marginals. And there's a theorem, an old theorem called Sklar's theorem, that applies to statistical objects called copulants. Probably Percy's theorem. Most of us have it. And copulants are just permutons, except that they could be higher dimension as well. And they're useful in statistics. And Sklar noticed that, yeah, no matter what distribution you have, you can make a transformation to change it to uniform distribution, and then you get what's okay. All right, so this is a picture of a, this is one that arises when you do random sorting methods. 3/4 of the way through random sorting. There's whole stories that go with permutons, which you won't hear here, but there's, I think they're great. All I'm gonna say. That would be the support for this permuton, so we know that that set can be the support. And so, for those of you who like puzzles, and include that I belong to the group, here's something to think about during the talk. Which of these sets is the support of it? I've even given them letters. So at the end of the talk, if you're willing to admit that you weren't paying any attention to the talk, raise your hand and tell me which letter you think is right. Okay. Finite distributions really are easy. As I said, they're very close to the classical problem, and it takes only a little tweak to get over that distance. Right. So we could think of them as row column sums, I was saying, or we could think of them as weights for the vertices of a backward. So here we have a template matrix, and we have given column sums across the top and given row sums along the right. And the problem is, okay, and the answer for this particular case is yes, but can we make a matrix which is positive where you see those ones and has those row columns? And equivalent problem, we have this little bipartite graph. The edges correspond to the one in that adjacency matrix there. And the weights of the vertices correspond to the column sums. And what are we looking for in this graph? We're looking for a full slope from the vertices on the left to the vertices on the right, and that we know what the condition for is. But we also want that flow to be nowhere zero. One positive edges where you see one and zero where you see zero. And okay, so how do we do that? Okay. Well, X is the vertices on the left, Y is the vertices on the right. And we'll just use graph notation. N of U is the neighborhood of U. We pick a bunch of vertices on the X side and look at their neighbors on the Y side, that's N of U. And we need this familiar Hall condition, which says that the weight of the neighborhood of a set is equal to the weight of the set. Otherwise, we can't have it. So, in the integer case, we have Hall's theorem, and we can deduce if there's a matching. But we're actually looking for less than that. We're looking for a flow. We can divide stuff up anyway. So that's an example of a neighborhood that's supposed to indicate the neighborhood is the set is expanding to go to the other side. To get the nowhere zero flow, you only need a simple second condition, which says that when you have equality in the Hall condition, then there can't be another element on the U side, which is mapped to N of U. Imagine there is, so here's a set whose neighborhood is the same size. So that's tight. And if we have an element that runs from somewhere else in U to that neighborhood, we won't be able to put any flow on that edge. So this condition, which is missing a parameter, which says that the size of the neighborhood of U is just the same as the size of U, in other words, U itself, is necessary, and it turns out it's the way I've stated these conditions They don't look symmetrical, but it's easy to verify that they were symmetrical. Okay, so today's proof. So I have to admit here that I was the guy who said 44 years ago, Leibniz, Austria, that a man-talk should have one proof and one joke. And that it should be possible to tell which is which. This is the proof. If you want a joke, that's fine. Okay, I want to show that these conditions are sufficient in the discrete case. We're going to be talking about a continuous case where you're not going to see proofs. You're not going to see whole proofs fitting into. Okay, so we define the slack of a set on the x side as the extra room we have on the y side. And so what do we do if we have a finite set? We can just look at the smallest slack, and that's not zero. And we pick any edge x, y, and we knock a little bit off of its weight at both ends. Now the idea is simple. We claim that the whole condition is still satisfied because any non-zero slack has just been reduced as still non-zero. And a zero slack is not a problem because the second condition tells us that we won't be able to find x outside the set, but mapping something in the set. And if that doesn't happen, then reducing the weight of this edge doesn't do any functions. So what do? We put in a flow which is just missing this epsilon piece. We do that for every edge, and we average out all these flows in there. Well, this is a simple proof, and it will be the outline of much more complex proofs in your case. All right. Side remark that you may not be aware of, that I wasn't when we started this, that there's a way to get what is, in a sense, the best flow in this distribution. And that is this. Imagine that the flow consists of lots and lots of tiny little packages. And I think these packages are going to be sent randomly to pick a point at x, package from there, goes randomly to any neighbor of x. But now you condition on the right number of packages arriving at each y to correspond to the weight of y. So this is set up a random thing, condition. And what often happens in large random systems, many of you know this phenomenon very well, is that when numbers start getting large, they behave in very predictable fashion. And in this particular case, if there are very many very small packages, the amount of flow in each edge will be essentially be predictable. And that amount of flow is the one that maximizes a certain entropy calculation that you can make for the flow. And that's just typical stuff, P log P minus or something. And so that flow will work to solve this problem, provided that your conditions satisfy the condition. Nice way to get the flow is by something called synchronous algorithm. And I see some nods like this. Yeah, it's a very nice algorithm where you try to balance all the rows and then try to balance all the columns that unbalances the rows. But it's provable that under these conditions, this converges actually pretty fast to this correct entropy maximizing distribution. Okay. Yeah. The infinite discrete case is just requires a little bit of tweaking to make it work. Here's the problem. We don't necessarily anymore have a minimum non-zero slack because there are infinitely many sets of them. And but it turns out that it's not a problem. And the nice way to do it is to show that the slack function itself is a submodular function. Has lots of nice properties. And one of them is that you can take limits. And if you take limits of sets whose slack approaches zero, you can get when the slack is zero. And then you can apply the second condition that we talked about and show that you haven't got a problem. So this, if you try to do this, you find that it works. What I've done here, as I've said, I wandered off a little bit into farther into network land. Lots of you are familiar with networks that have capacities on the edges. And there's a capacitated version of this theorem. And for this, you just have to be careful. And when you're applying Hall's condition, instead of using the weight of y, we use the minimum of the weight of y and the total amount of capacity of the edges from x to that vertex. Then if you restate the conditions in the obvious way, you get something which works for capacitated flows even at infinite, but still discrete. All right. Yeah, so this is what the conditions then look like. All right, what about the continuous case? Well, part of it is easy. It's actually the part of the discrete part that's the easiest as well, which is that if all you want is a coupling of your random variables whose support is inside the given set x, and all you need is the whole condition stated in terms of a Lebesgue measure. Take a subset of x, you project it up to your, you inverse project it up to your set, and then project it over to y. That gets you the neighborhood of x, neighborhood of the set u. And then you just compare the Lebesgue measures, and you're good to go for having something that's supported in S. But we want something which is supported exactly by S. So what can we do? Let me back up just one little bit. I was talking to Spencer earlier, a little while ago, who asked about, does this mean you get a continuous version of Maxwell main cut? And the answer is that you do. And we use that to, this is just a special case of that continuous version. Continuous version works a little bit like this, in case you might find it useful. You're given two marginal distributions outside of beta, which might not be probability distributions. They might have some other total mass. And then what you do is you find the subset of x, which minimizes beta of the neighborhood of the subset plus alpha of the complemental subset. All this makes sense. You think of this in terms of what a cut should look like in this case. And turns out that you always can find such a set. You don't need to think the one that realizes this thing, and it gives you capacity C. And now the theorem says that that you can find a distribution on the set in your unit square, which has that total mass, and whose marginals are bounded by the given marginal dominant. All this is very straightforward. Now to the less straightforward part. Yeah, we like to characterize the sets that exactly support. And to start with, we look at regular sets. So a regular set is just a set which a regular closed set is just a set which is the closure of its interior. Right? Most of the sets that you draw, if they have an interior, would have this property. And many of the permutons we're interested in have. And for that, you will need something like the second condition. And indeed, the second condition translated to the vague measure basically works. If it's true that whenever the neighborhood of the set has the same Lebesgue measure as the set itself, so it's a tight set, then if you go back the other way, you take the neighborhood of the neighborhood, you get a set that's the same size as the second star. I want to give you a little bit of an idea of how this is. Okay. So we want to use as an outline the method we used before. We're going to knock off measures from something, show that the whole condition is still satisfied, and add it back on to try to get the subordinate cover the given set S. But here it's tricky because it's not a question of single points. It's a question of areas, we call them cells, inside the unit square. And so we want to show that if we have such a cell that's inside the set S, then we can get a permuton which has mass on the cell. And if we can do this for every cell, then we can put these all together to make a permuton that covers the whole set S. Okay, but doing this is a little bit tricky, and again, we make use of some nice properties of suboptionality. We define something called the torque. So we look at have the cell has size which we call I and J. And what we want to do is we want to knock off a little bit of marginal from J and from I without disturbing the whole property. How can we get away with this? Well, if we pick a subset of one of the sides of the cell, we have to look over all sets whose slack could be made negative by shaving off an amount. And that defines a quantity that we call torque, which is in a sense dual to slack. And I'm not going to take you through the definitions, that would be crazy, but they exist. And we use two great properties that we can show that the torque of the whole side of the cell is positive. So that at least gives us a chance to put some mass in the cell. And very importantly, torque can also be shown to be a submodular function. And submodular functions have this wonderful property that they contain distributions underneath them which have the same mass as the total mass of that submodular. So in a way, a submodular function is a super distribution, it lies over a distribution. And this is something which has appeared in Lovaas's work, discrete stuff, but it's really fairly elementary and easy to prove in the continuous case as well. So we end up with a probability distribution that we shave off this side, and we can shave off that side. We still satisfy the whole condition. We put a subpermuton on, and then we can find a distribution that has the right marginals on the cell, put that back in. So, yeah, what about the general case? The general case is a little bit shocking. We have the following problem. Two conditions are not enough. And here's an example of a set which satisfies the two conditions. But it can't be the support of the permuton because if we put any measure on that horizontal line in the middle of the hole, that would cast the shadow, which is more than Lebesgue measuring the right hand side. But it turns out that the obvious way of avoiding that is also not. When we came down to a stronger necessary condition, which says that there may not be what we call a wild set. This is a picture of a graph of a function. And it's possible to have the following annoying thing happen. That there's a subset of x of the bottom of this thing, which is full measure. And its neighborhood on the right, if you project it through this curve, has 0 measure. If that happens, we're dead. And so this is a necessary condition. We think it's sufficient, but we haven't proved it. Any ideas? Richard, you'll see, looking around, find me at the meeting, let me know.
I'm skeptical.
You're skeptical. Yeah, I mean, these measures can really be off. Sets can be awful. I understand, you feel like maybe right. Okay, and okay. This, by the way, does anyone want to try guessing? That is not the supported term of the Krypton. That one is, this one is, but that isn't. This one isn't. That one is. This one is, and that. There you go. All right. Thank you for your attention and happy birthday, Rich.
Thank you, Peter, for the wonderful talk. Any questions?
Yeah, can you explain the answer?
Can I explain what?
The answer.
Oh, can I explain the answers? Very briefly. Very briefly, I'll go back. Yes. The circle fails the second condition. But the disk actually is supporting a well-known permuton that you get by projecting the uniform probability distribution of a sphere down to the inscribed circle. In this case, again, they both satisfy the Hall conditions, but now you need the stuff in the middle. In this case, if you just check the Hall condition, you see that this guy fails. This guy passes. And in the last case, well, it turns out that when you have a curve, when you have curves in your box, and you apply the conditions, that they tell you something, they come down to checking something about the derivative of the curve. In this particular case, the derivative of the curve goes under a half. That causes a violation of the Hall condition. In this case, it doesn't. What can I tell you?